Welcome, everyone. We're diving deep today into a fascinating period in particle physics. The evolution from a bunch of different models to the unified elegance of the standard theory.
A compelling journey, to be sure.
Our guide for this exploration is a research paper called From Many Models to One Theory, From the Dark Ages to Enlightenment by J. Iliopoulos.
A fitting title.
Absolutely. It kind of sets the stage, doesn't it?
It does, yeah. The paper commemorates two significant anniversaries, actually the 70th anniversary of CERN and the 50th anniversary of discovering the J particle.
Both landmarks in the field. And for our deep dive, we're going to zero in on gauge theories, their origins, the challenges they presented, and ultimately their triumph in shaping the standard model as we know it. Now, Iliopoulos describes theoretical physics in the 1950s and early 60s as the Dark Ages.
He does, yeah.
Can you kind of paint a picture of what he means by that?
Well, think of it as this. Physicists were grappling with what he calls a double failure.
Okay.
So on the one hand, you had these infinities popping up in perturbation theory calculations.
Right.
And these infinities, well, they just threw theoretical predictions into chaos, questioning the validity of quantum field theories themselves.
So basically, the math was just falling apart at the most fundamental level.
Exactly.
And what about the other failure? What was that all about?
So there was also this lack of non-trivial solutions that satisfied the Whiteman axioms.
Right, the Whiteman axiom.
These axioms, well, they're basically a set of mathematical conditions that were, and still are, considered essential for a consistent quantum field theory. And failing to meet these axioms, well, it just signaled deeper issues with the theory itself.
Adding to the whole mess, the paper mentions a disconnect between different areas of research.
Yes, it was like researchers were speaking different languages.
Really?
Yeah, strong interaction processes. Those were mainly investigated through the lens of the S-matrix's analytical properties, while weak interactions, they relied heavily on Fermi theory.
So no common framework, no way to connect the dots.
Exactly, which hindered progress, of course.
So a time of fragmentation, lots of uncertainty. But it's interesting how from these dark ages, as he calls them, the seeds of gauge theories began to sprout.
It is, yeah. And the concept of gauge invariance itself actually, it has its roots way back in classical electromagnetism. The theory shows a remarkable kind of invariance under specific transformations of the vector and scalar potentials. And those are what we call gauge transformations.
Meaning the equations stay the same even after these transformations.
That's right. Exactly.
That's wild.
Yeah. Initially, this whole invariance thing, it was seen as a mere mathematical curiosity. But little did they know its profound implications would later completely revolutionize how we understand fundamental forces.
In general relativity, our theory of gravity, that itself emerged as a gauge theory as well.
Yes, it did. General relativity shows an invariance under local translations, basically changes in the coordinate system used to describe spacetime. So this expanded the scope of gauge theories beyond just electromagnetism, suggesting a deeper connection between these symmetries and fundamental forces.
So from classical physics all the way to the quantum world, gauge theories were taking root.
They were, yeah. In 1926, shortly after Schrödinger came up with his wave equation, Fock in London, they independently made a pretty crucial observation. They noticed that the U1 global symmetry of the Schrödinger equation, the equation governing how quantum particles behave well, they realized it could be linked to electromagnetism.
Meaning this abstract mathematical symmetry in quantum mechanics had a direct connection to a real physical force.
Yes, precisely. It was a real turning point because it suggested this deep connection between symmetries in quantum mechanics and the fundamental forces of nature.
Wow.
And then, in 1929, Weil extended this concept of gauge invariance to the Dirac electron, which is a relativistic description of the electron,
Okay.
bringing in both quantum mechanics and special relativity into the mix.
His work must have been groundbreaking.
Oh, it was. It really was. He brought in concepts like Weyl spinors, mathematical objects that are used to describe particles with spin, and the Vierbein formalism, which connects the geometry of space-time with its coordinate description.
Right, the Vierbein formalism.
These advancements really expanded our mathematical toolkit, for understanding particle physics.
It's amazing how these seemingly abstract mathematical concepts laid the foundation for such a revolution in physics. And now things start to get, well, a bit more complex with the introduction of non-abelian gauge theories.
You do, yeah.
What does non-abelian even mean in this context?
Well, Non-abelian simply means that the order in which you perform the symmetry transformations actually matters, unlike in electromagnetism.
Okay.
It added a layer of complexity for sure, but it also enriched the theory in a lot of ways.
And these non-abelian gauge theories, we can thank Yang and Mills for those.
Exactly. In 1954, Yang and Mills proposed a really groundbreaking generalization of gauge theories to non-abelian symmetries. Their work would deeply impact our understanding of fundamental forces, but not without some challenges along the way.
The paper mentions these roadblocks they faced in applying Yang-Mills theories to weak interactions.
Yeah, there were two main ones, really. Firstly, you had the ever-present problem of renormalization.
Right.
As we talked about before, those perturbation theory calculations often resulted in infinities.
And just to remind everyone, renormalization is a mathematical technique for handling those infinities.
Exactly. And extracting, meaningful physical predictions. But applying renormalization to these Yang-Mills theories, well, it proved to be much more challenging than in something like quantum electrodynamics.
Much more challenging.
Yeah. It required new techniques like the Gupta-Bleuler method
Right.
for quantizing gauge theories while preserving Lorentz covariance. That means making sure the theory looks the same no matter the observer's reference frame. And then you had the Pauli-Villers regularization. That introduced these auxiliary fields to regulate the infinities popping up in the calculations.
So basically, new tools were needed to make the math work, but also respect the principles of gauge invariance in quantum mechanics.
Precisely. And the second hurdle involved applying Yang-Mills theories to strong interactions. Early attempts by Klein in 1938 and then Pauli in 1953 to construct an SU2 gauge theory for strong interactions, well, they failed.
Why? What went wrong?
Well, looking back, their approach was a bit off, really. They were trying to derive the SU2 gauge theory as a limit of a higher dimensional theory of gravity,
Okay.
essentially forcing a connection between strong interactions and gravity. And now we know, of course, that doesn't exist.
A classic case of searching for a connection where there wasn't one. But despite these initial setbacks, the seeds of a really powerful theory had been planted.
They had, yeah. And the story of renormalization itself is a fascinating one.
Tell me about it. It wasn't immediately embraced, right? Not even by giants like Feynman and Schwinger.
No, not at first. They actually saw renormalization as kind of a mathematical trick, an ad hoc solution instead of a fundamental part of the theory. But its success in quantum electrodynamics, well, was undeniable.
It was.
It led to incredibly precise predictions that matched experimental results with astounding accuracy.
So the effectiveness of renormalization in QED, it eventually won over even the skeptics.
It did, yeah. Now, before we go deeper into the complexities of renormalization and applying it to Yang-Mills theories, let's look at another fascinating concept that emerged around this time, the axial anomaly.
Okay, the axial anomaly.
Yeah.
This is where things get even more, well, counterintuitive in quantum field theory.
That is, yeah. The axial anomaly is this quantum effect that reveals a subtle violation of a classical conservation law.
Okay.
In classical physics, certain quantities like energy or momentum, angular momentum, they remain constant over time. They're conserved. But quantum mechanics can throw in some subtle modifications to these classical conservation laws.
So the axial anomaly basically shows that the quantum world doesn't always follow those rules of classical physics.
Right.
Got it.
And the story of its discovery is quite interesting.
Yeah.
It starts in 1949 with Steinberger. He stumbled upon what we now know as the axial anomaly while he was calculating the lifetime of the neutral pion.
Okay.
Then, in 1967, Sutherland derived a theorem based on current algebra. It implied this startling result. The electromagnetic decays of neutral mesons, things like the pion, should be forbidden if chiral symmetry was exact,
Chiral symmetry.
a type of symmetry related to the left and right-handedness of particles.
Okay.
But this contradicted what we saw in experiments. We knew that neutral pions did decay electromagnetically, so there was this conflict between Sutherland's theorem and reality.
Right. So how do you reconcile that?
Well, that's where Bell and Jackie come in.
Oh, okay.
In their famous 1969 paper, Bell and Jackie tackled this head-on. They showed that Sutherland's theorem, while valid in classical physics, it was actually violated at the quantum level due to this axial anomaly. And they demonstrated that this quantum effect, it had real-world observable consequences.
So the axial anomaly wasn't just a mathematical quirk. It's a fundamental aspect of quantum field theory with real-world implications.
Exactly. Their work played a key role in reconciling those theoretical predictions with what we observed in experiments.
Fascinating. This brings us to another big concept. Spontaneous symmetry breaking.
Yes.
Why is this so crucial to the Standard Model?
Well, spontaneous symmetry breaking, or SSB for short, it's essential for understanding how particles acquire mass.
How can the symmetry be broken spontaneously, though? It sounds counterintuitive.
Okay, think of a pencil standing perfectly upright.
Okay.
It's symmetrical, right, under rotations around its axis.
Yeah, I see that.
But this symmetry, it's unstable. Even the slightest nudge and the pencil falls over, breaking the symmetry.
Right.
So the system kind of chooses a particular direction, breaking that initial symmetry.
So this same principle applies to the fundamental forces.
Precisely. The equations might be symmetrical, but the solutions to those equations might not be. Take the electroweak force, for example.
Okay.
At really high energies, the theory has perfect symmetry between electromagnetism and the weak force. But at lower energies, the symmetry spontaneously breaks.
And this breaking is tied to how particles get their mass.
Exactly. The way this symmetry breaks determines the masses of those force-carrying particles. Things like the W and Z bosons, they mediate the weak force, and then you have the photon, which mediates electromagnetism.
So it's SSB, spontaneous symmetry breaking, that gives these particles their unique masses, even though they originate from this unified force. The paper talks about different ways this symmetry breaking can show up, the Wigner and Nambu-Goldstone realizations.
Yeah, it does. The Wigner realization is pretty straightforward. The symmetry is there, right, in the spectrum of particles. Particles related by the symmetry have the same mass. A good example is the proton and the neutron. They're related by isospin symmetry, and they have almost identical masses.
And the Nambu-Goldstone realization, what's different there?
Well, in that one, the symmetry is, in a way, hidden.
Hidden.
Yeah, instead of these, degenerate particles, you get these massless particles called Goldstone bosons. This was a crucial insight for understanding how particles acquire mass in these gauge theories.
So breaking symmetry can actually lead to the creation of new particles.
It can,
The paper also highlights the role of superconductivity in understanding SSB.
It does, yeah. Superconductivity, where some materials have zero electrical resistance at very low temperatures, provided really valuable insights for particle physics. In superconductors, SSB explains this thing called the Meissner effect. It's where magnetic fields are expelled from the material's interior.
Okay.
The breaking of a symmetry related to electromagnetism, well, that's what leads to this remarkable behavior.
So a seemingly unrelated phenomenon offers clues about how fundamental forces work.
That's right.
Fascinating. And then we have the Brout-Englert-Higgs mechanism, the BEH mechanism, which has become synonymous with giving particles their mass.
Yes, it has. The BEH mechanism, it's basically a way to give mass to these force-carrying particles without messing with gauge invariance. Remember, adding mass terms directly to the equations, well, it breaks that crucial symmetry.
Right.
The BEH mechanism elegantly sidesteps this problem by introducing a new scalar field that permeates all of space.
Okay.
The scalar field, it interacts with those force-carrying particles.
Right.
And through this interaction, they acquire mass. It's like the scalar field is this cosmic molasses imparting mass to particles moving through it.
I like that analogy.
Right? It works well. And the beauty is that this mass generation, it happens without breaking the underlying gauge symmetry of the theory.
The paper credits Anderson, Schwinger, and others for exploring this connection between gauge invariance and mass generation.
They did, yeah. Their contributions were really critical in paving the way for the BEH mechanism. And then in 1964, Englert and Brout, independently of Higgs, proposed a model using elementary scalar fields to generate mass for gauge bosons while, keeping that gauge invariance. Their work was a major breakthrough.
And what about Higgs? Where does he fit in?
Higgs, also in 1964, independently arrived at a similar mechanism. His work emphasized the role of the scalar field's vacuum expectation value, essentially the average value of the field throughout space,
Right.
in determining particle masses.
So the BEH mechanism wasn't a solo effort. It was years of research, a culmination of brilliant minds coming together.
Exactly. It provided a solution to this long-standing puzzle of how to give mass to force-carrying particles, without sacrificing the theoretical framework. And this breakthrough paved the way for the Glashow-Weinberg-Salam model,
The GWS model.
which unified the electromagnetic and weak forces into a single electroweak force.
This unification, I assume, only happens at high energies,
It does, yeah. But at lower energies, the symmetry breaks spontaneously,
as we talked about before.
leading to those separate electromagnetic and weak forces we observe. And this model, well, it incorporates the BEH mechanism, right?
Right, it does. The W and Z bosons gain mass by interacting with the Higgs field, but the photon stays massless.
Exactly. The GWS model gave us a consistent, experimentally validated description of both electromagnetism and the weak force.
This is the foundation of the electroweak sector of the Standard Model, the model that covers our understanding of all fundamental forces, except gravity.
It is, yeah.
Now, the paper also mentions the GIM mechanism as a key part of the GWS model.
It does, yeah. The GIM mechanism, named after Glashow, Iliopoulos, and Maiani, it was proposed in 1970. It was meant to address the problem of flavor-changing neutral currents. Flavor, you see, is a quantum number that distinguishes different types of quarks.
Right, different flavors of quarks.
The GIM mechanism introduced a fourth quark, known as the charm quark.
Ah, to suppress these unwanted currents.
Exactly, and this prediction was later confirmed experimentally.
So not only did it solve a problem, but it also predicted a new particle. That's incredible.
It is. And now our journey takes us to the realm of the strong force and the development of quantum chromodynamics.
QBCD.
Yes. This theory describes the interactions between quarks and gluons.
Right, the fundamental particles that make up protons and neutrons.
Yeah, they're hadrons, too.
Right, hadrons, those composite particles made of quarks. So gluons, I take it, mediate the strong force, just like photons mediate electromagnetism.
Exactly, you got it. QCD is really interesting because it's an example of an asymptotically free theory.
Asymptotically free. What does that mean?
It means the strength of the strong force, it actually gets weaker at higher energies or shorter distances.
So the closer the quarks, the weaker the force. That's kind of counterintuitive, isn't it? I mean, the strong force is supposed to be what binds them together in hadrons.
It is, yeah. This seemingly paradoxical behavior, well, it was one of the key puzzles that physicists needed to explain, and QCD did that.
It did.
Yes, its property of asymptotic freedom provided that explanation.
It's amazing how this theory can explain this dual nature of the strong force.
It is, yeah. It can explain why quarks appear both strongly bound and almost free, depending on the energy of the interaction.
The paper mentions deep inelastic scattering experiments at SLAC.
It does, yeah.
They played a crucial role in this whole understanding of strong interaction.
A crucial role. In these experiments, they fired high-energy electrons at protons and neutrons.
Okay.
And what they found was really revealing. They discovered that these particles weren't fundamental. They were composed of these point-like constituents.
Constituents.
Yeah, which Feynman later called partons. And these partons would eventually be identified as quarks.
So these experiments basically gave the first concrete evidence for quarks.
They did, yeah. But they also revealed something really puzzling.
What was that?
Well, the quarks inside these protons and neutrons, they seemed to behave almost like free particles when they were probed at high energies.
But they're supposed to be bound together.
Right. This apparent contradiction, well, it required a theoretical framework that could accommodate both the strong binding of quarks within hadrons and their seemingly free behavior at high energies.
And that framework was QCD.
Exactly. QCD was the answer.
It's remarkable how QCD can explain both sides of this coin. The quarks being both strongly bound and seemingly free depending on the interaction.
It is. And its success didn't stop there. QCD went on to accurately predict and explain many other experimental observations, like the properties of tarmonium spectroscopy,
Okay.
which involves studying particles made of a charm quark and a charm antiquark.
Right.
And it explained those scaling violations seen in deep inelastic scattering experiments.
Where certain quantities deviate a bit from a simple scaling behavior.
Exactly. These successes solidified QCD as the correct theory of the strong force. But what's truly remarkable, is the elegance and depth of QCD as this non-abelian gauge theory.
Meaning the order of the symmetry transformations matters.
Yes. And this non-abelian nature, while it adds complexity, it's what gives rise to some of QCD's most remarkable properties.
Such as?
Asymptotic freedom, which we've discussed.
Right.
And also confinement.
Confinement, that's the idea that we never see quarks in isolation. They're always bound within hadrons.
Precisely. These two seemingly contradictory properties are actually both consequences of the same underlying theory, which is a real testament to the power and elegance of QCD.
So from this intricate world of hadrons and their interactions, QCD really distilled the essence of the strong force.
It did, yeah. It revealed this fundamental symmetry and a set of rules governing the behavior of quarks and gluons.
And its inclusion in the Standard Model, that was a big win for particle physics, wouldn't you say?
A big win. It gave us a deep and comprehensive understanding of one of the most fundamental forces in the universe.
Incredible.
That is.
Well, this brings us to the end of this part of our deep dive. We've come a long way, haven't we? From those dark ages to the emergence of a unified and powerful framework for understanding particle physics.
We have.
We've seen how theoretical insights, guided by experimental observations, led to the development of these incredible theories.
Yeah.
Gauge theories, the theory of renormalization, the concept of spontaneous symmetry breaking.
All crucial pieces of the puzzle.
And we've witnessed those groundbreaking discoveries, the experimental confirmation of key predictions like the W and Z bosons, the top quark, gluon jets, and of course, the Higgs boson.
A lot of remarkable achievements, all pointing to the validity of the Standard Model.
They do. It's a story that highlights the power of the scientific method, the collaborative spirit of the physics community. It's really inspiring.
Last time we navigated that Dark Ages period of particle physics, a time of fragmentation and uncertainty. Now, let's see how the field emerged from that and entered this period Iliopoulos calls the Enlightenment, marked by the growing acceptance of the Standard Model.
Right, the Enlightenment.
A pivotal moment in this transition was the 1974 London Conference on High-Energy Physics.
The 1974 London Conference.
Iliopoulos describes it as a turning point where the evidence really started to favor the Standard Model.
What made this conference so important?
Well, two major discoveries were announced at the conference.
Okay.
First, the Gargamel collaboration at CERN presented evidence for neutral currents.
Neutral currents.
Interactions mediated by the Z boson.
Right, the Z boson.
Which, of course, was a particle predicted by the GWS model.
So a particle predicted by theory was finally observed. That's big.
Big, yeah. It lent strong support to the electroweak framework.
Right. And the second key finding, what was that?
Data from electron-positron collisions hinted at the existence of charmed particles.
Charmed particles?
Particles containing the charm quark.
Okay.
Another prediction from the GEM mechanism.
Right, the GEM mechanism.
These discoveries, they were like pieces falling into place. They really bolstered that theoretical foundation that had been built.
It's like things were starting to click.
Exactly.
Iliopoulos even mentions his own bet on the discovery of charmed particles.
He does, yeah.
Toasting to charm at the conference.
The charm.
It really captures that excitement, that feeling that something big was happening.
It does, yeah. It marked a shift from cautious speculation to, a growing sense of inevitability. The feeling that the Standard Model was truly on the right track. But of course, more evidence was needed to really solidify its standing.
Of course. And in the years that followed, there was a whole cascade of groundbreaking discoveries that further cemented the Standard Model's position, starting with the W and Z bosons, those force carriers of the weak interaction.
Right.
Responsible for things like radioactive decay.
Exactly. Their existence was a cornerstone prediction of the GWS model. And in 1983, they were directly observed at CERN's superproton synchrotron.
A huge confirmation of the electroweak theory.
A monumental confirmation.
Another milestone was discovering the top quark, the heaviest of all the quarks.
Yes. It was predicted to complete the third generation of quarks.
Right, we had the up and down quarks.
The sharp and strange quark.
And the bottom quark.
And the top quark was the missing piece.
The missing piece.
After years of searching, experiments at Fermilab finally observed it in 1995.
Amazing. These discoveries, along with observing gluon jets, those sprays of particles that signal the presence of gluons, the force carriers of the strong interaction,
right,
they really added weight to the Standard Model.
They did. Gluon jets provided direct evidence for gluons. Before that, they were only inferred indirectly, so observing them really solidified QCD as the theory of strong interactions.
And finally, in 2012, the Higgs boson was discovered at the Large Hadron Collider.
Higgs.
That elusive particle responsible for giving mass to other particles.
Through the BEH mechanism.
Right, the BEH mechanism was the final piece of the Standard Model puzzle.
It was a remarkable feat of scientific ingenuity and collaboration.
Absolutely. And it confirmed the mechanism by which particles get their mass.
A resounding confirmation.
All these discoveries, spanning decades, they represent a remarkable synergy between theoretical and experimental physics.
A synergy, yeah. Each discovery added another piece to the puzzle,
revealing a more complete picture of the universe's fundamental building blocks.
It really shows the power of the scientific method, where theoretical predictions are rigorously tested. And the Standard Model emerged from that rigorous testing as a remarkably accurate and predictive theory.
But as we've mentioned, the story doesn't end there. The Standard Model has its limitations.
It does.
It doesn't explain things like dark matter and dark energy, the origin of neutrino masses.
Or the unification of gravity with the other forces.
Right, big questions. So the Standard Model, while incredibly successful, it's not the final word.
No, it's not. But its success has given us a solid foundation to build on.
A foundation.
And these open questions, they continue to drive research, pushing us to explore new theoretical frameworks.
Iliopoulos makes an interesting point about the acceptance of the Standard Model. He says it wasn't just about accumulating enough evidence, it was a more fundamental shift in perspective.
He's right. It wasn't just checking off boxes until the theory was proven. It was a change in how physicists saw the roles of theory and experiment.
A change in perspective.
Moving away from a focus on phenomenological models.
Which describes specific phenomena without a deeper framework.
Right, to a more unified, fundamental approach. With gauge theories and the Standard Model, physicists started to see the connections between seemingly separate phenomena.
And the Standard Model, with its predictive power and encompassing framework, provided a more complete picture.
A more satisfying picture of the universe.
And this shift, this change in perspective, that was key for its widespread acceptance.
It was, yeah.
It highlights that dynamic interplay between theory and experiment in shaping our understanding.
It does. And nowhere is this interplay more evident than in the evolution of our understanding of strong interactions.
Strong interactions.
Right.
Right. In the early days, the main approach to studying strong interactions involved analyzing the S-matrix.
The S-matrix, which describes the probabilities of different outcomes in particle collisions.
Right. It was a useful tool, but it lacked a fundamental theory explaining the mechanisms at play.
It was more descriptive than predictive.
And this lack of a fundamental theory held things back.
It did, yeah.
There were also a bunch of phenomenological models, each tailored to specific aspects of strong interactions, but they lacked that unifying framework to connect them.
It was like having puzzle pieces without the picture on the box.
And then came those deep, inelastic scattering experiments.
Which revolutionized our understanding.
These experiments showed that protons and neutrons weren't elementary particles.
They were made up of these point-like constituents, quarks.
But they also uncovered that strange duality.
Where the quarks inside these particles seem to behave almost like free particles at high energies.
Even though they were bound within the hadron.
It was a major puzzle. It challenged the view of quarks as strongly bound entities.
And it demanded a new theoretical framework.
It did, and that framework was QCD.
With its property of asymptotic freedom.
Exactly. Asymptotic freedom explained why quarks could appear both strongly bound and almost free, depending on the energy of the interaction.
So QCD solved that puzzle of the strong force's dual nature.
It did. It elegantly explained why quarks could be confined within hadrons, yet behave as if they were free at high energies.
Incredible.
Yeah.
And its success went beyond just resolving that paradox. QCD accurately predicted a whole range of phenomena.
It did. From the properties of hadrons to the behavior of quarks and gluons in high-energy collisions.
So from a landscape of phenomenological models, QCD emerged as a unifying predictive theory of the strong force.
And further solidified the Standard Model as a remarkably successful framework.
It's a story of collaboration, of brilliant minds coming together.
Challenging assumptions, pushing the boundaries of knowledge.
But what makes QCD so elegant is its foundation as a non-abelian gauge theory.
Right. The order of those symmetry transformations matters.
This non-abelian nature, it adds complexity but also gives rise to those remarkable properties.
Like asymptotic freedom, which explains the quark's apparent freedom at high energies, and confinement.
Right, confinement, ensuring we never see quarks in isolation.
Exactly. Two seemingly contradictory features, both consequences of the same theory, a testament to QCD's elegance and power.
So from this complex world of hadrons, QCD distilled the essence of the strong force.
Revealing that fundamental symmetry.
And a set of rules governing quarks and gluons.
Its integration into the Standard Model was a major triumph.
Providing a deep understanding of one of the fundamental forces shaping our universe.
It was.
It's been quite a journey, hasn't it? We've gone from the fragmented Dark Ages to the elegant unification of the Standard Model. This framework truly represents our current understanding of particle physics.
It has been a remarkable journey. From those initial struggles with infinities, and the search for a unifying language, to discovering fundamental particles and confirming these groundbreaking theories, it really speaks to human curiosity and ingenuity.
Absolutely. As we wrap up our deep dive into Iliopoulos' paper, I want to highlight one more crucial aspect. This underpins the entire journey. The profound role of mathematics in shaping how we understand the universe.
Yes, mathematics is more than just a tool. It's the language of physics. It gives us the framework to express the laws of nature with precision and elegance. I mean, without the rigor and abstraction of mathematics, our understanding of particle physics would be, well, severely limited.
Iliopoulos mentions several mathematical concepts that were essential in developing the Standard Model, things like gauge transformations and renormalization.
He does, yeah.
Can you unpack how these abstract mathematical ideas translated into concrete physical understanding?
Sure. Let's start with gauge transformations.
Okay.
These are mathematical operations that essentially change our perspective on a physical system, but without actually changing the underlying physics. Imagine looking at a spinning top.
Okay, a spinning top.
It doesn't matter what angle you view it from. The top is still spinning, right?
Right, it's still spinning.
Gauge transformations are like changing our coordinate system, but without affecting the physical reality we're trying to describe.
So gauge transformations are like shifting our viewpoint without changing the underlying physics.
Precisely. In gauge theories, the requirement of invariance under these gauge transformations, meaning the physics shouldn't change even after these transformations, well, that leads directly to the concept of force.
So the forces we observe in nature, are they a result of needing our theories to be invariant under these specific mathematical transformations?
Exactly. It's a profound connection between symmetry and force. And it's a cornerstone of how we understand particle physics today. Gauge invariance dictates the existence of those force-carrying particles, like photons, gluons, the W and Z bosons.
Wow. So this abstract mathematical requirement directly corresponds to the forces that shape the universe as we know it.
It does.
And then we have renormalization. This was about tackling those pesky infinities in calculations.
Right. Those infinities were a major headache for physicists early on. They seemed to suggest that the theory itself was flawed. But then renormalization came along and provided a rigorous framework for dealing with them and extracting meaningful physical predictions.
But it wasn't just about applying a mathematical trick, was it? Iliopoulos emphasizes that renormalization involved a deeper shift in how we understand physical parameters, things like mass and coupling constants.
He's right. It wasn't just a technical fix. It was recognizing that the values we measure for these parameters in experiments, well, they're not the same as the bare values that appear in those original equations. Renormalization essentially dresses these bare values. It takes into account the quantum fluctuations that affect them.
So our measurements are affected by the way we're observing the system. It's like the act of observing influences what we see.
That's a good way to think about it. Renormalization gave us a way to reconcile the theory with what we observed, making quantum field theory a consistent and predictive tool.
Another great example of how math guides us toward a deeper understanding of the physical world. And this interplay between these abstract mathematical concepts and real physical phenomena is also clear in the concept of spontaneous symmetry breaking.
It is, yeah. As we discussed, spontaneous symmetry breaking happens when the equations describing a system are symmetrical, but the solutions to those equations aren't.
Like that pencil standing upright, with its rotational symmetry until it falls over.
Exactly. In particle physics, this explains how particles get their mass through the BEH mechanism. The Higgs field, which is everywhere, it breaks the electroweak symmetry. This gives mass to the W and Z bosons, but leaves the photon massless.
So the mathematical concept of symmetry breaking has a direct physical consequence. It determines the masses of fundamental particles.
Precisely. And this highlights a key theme throughout the development of the Standard Model. This profound connection between mathematical elegance and physical reality.
It really is remarkable. The pursuit of mathematical consistency and beauty, it can lead to such profound insights into how the universe works at the most fundamental level.
It can. And this journey isn't over. These mathematical frameworks we've developed over the years, while they led to the Standard Model, they've also opened up new avenues.
Like what?
Things like string theory, supersymmetry. These seek to unify all the forces of nature, including gravity.
So the Standard Model, as successful as it is, it's not the final word.
It's not. It's a stepping stone toward an even deeper, more complete understanding of the universe.
It's a testament to the power of the scientific method, isn't it?
It is.
Each new discovery brings new questions,
It does.
pushing us to explore uncharted territory.
It does. The mysteries of dark matter, dark energy, neutrino masses, the unification of gravity, they're all waiting to be unraveled.
And as we keep probing deeper into the fabric of reality, mathematics will be our guide, providing the language and the framework to express the profound beauty and elegance of the cosmos.
The universe is a vast and complex tapestry, woven from these threads of fundamental forces, particles, and symmetries. And as we continue to explore its intricate patterns, I'm sure there are more surprises waiting for us, more profound insights, more breathtaking discoveries.
Absolutely. And that concludes our deep dive into this fascinating history of particle physics and the development of the Standard Model. We hope you've enjoyed exploring the subatomic world with us, and maybe gained a deeper appreciation for the remarkable achievements of modern physics. Until next time, keep questioning, keep exploring, and keep seeking knowledge. The universe is full of wonders waiting to be discovered.